Hello friends, this video on DNF block elements part 25 is brought to you by examfear.com. No more fear from exam. Of D block elements where we talk about the interstitial compound. So what are the interstitial compound? I think we have studied about this interstitial compound. See, interstitial compounds are those compounds which are formed when small atoms like hydrogen, carbon, nitrogen, all these are small atoms. These small atoms are trapped somewhere here. So if you see small atoms here, for example, this places, these are all small atoms. Sometimes they are trapped. This is the NaCl crystal. I mean, it can be any crystal. So let's suppose there's a crystal of metals, and in this crystal, these small atoms are trapped. Okay. Now, since these metals are just trapped, there is no actual bonding. So they are usually non-stoichiometric. Okay. Once again, since they are just trapped and there is no bond, so they are generally non-stoichiometric. For example, TiH 1.7. That is, for every one titanium, you have 1.7 hydrogen. They are just trapped. Okay, and these non-stoichiometric compound, if you want to define, they are the chemical compound that can't be represented by a ratio of well-defined natural number. For example, CO2. It's a well-defined natural number. This is TiH 1.7, not a well-defined natural number. These are non-stoichiometric compound, right? Typically, in this case, small molecules are trapped, and they are trapped in any ratio. They don't have a proper bond. Okay, but they have different properties. This interstitial compound, they have high melting point and boiling point than that of pure metals. They are very hard. They have the hardness similar to diamond also. They are chemically inert. Chemically, they are inert, and their metallic conductivity is retained, but their ductility and malleability is reduced. That is reduced. See, this is my structure. We have discussed these structures in the past few chapters. So here, some of the small molecules like carbon, nitrogen are trapped. Okay, if you want to visualize in this fashion. So they are trapped, the whole formula changes, and it's all non-stoichiometric. You can also say these are non-stoichiometric defects also. The next is alloy formation. See, alloy formation is almost similar as the interstitial compound, but here we have the mutual substitution of atoms. So here, if let's suppose one atom is replaced actually, so you want to introduce one has to go out. Okay, so since now there is a difference. See, in case of interstitial, we were using small atoms like carbon, nitrogen, right, or hydrogen. These were small atoms. These were occupying the extra space here, right? Extra space here. That was interstitial compound. But in this case of alloy formation, we are saying if I am introducing an atom, one atom has to be replaced. That means the new atom should be of comparable size, right? It should also be of the comparable size. For example, this red one, it can actually replace this gray one. Okay, so this is the new atom, and that's what we do. So if we talk about definition of alloy is nothing but the blend of metals prepared by mixing various metals, and they are homogeneous solid solution in which atoms of one metal is actually distributed randomly across the atom of another metal. For example, copper and zinc. Copper and zinc, the size is almost same. So copper can replace zinc atoms in the lattice. Okay, so there is you just can't form alloy for any two metal or any two element. The size of the atom should match. You can't form an alloy of copper and hydrogen. Not possible. But you can form an alloy of copper and zinc. That's why you see when you talk about alloy, you talk about alloys of typically metals of similar size. Okay, so plus minus 15% is okay, but yeah, that's what the range we are looking for. For example, this is 100 picometer. It can be 100 or 85 to 115 picometer. I'm just taking two elements, X and Y. That should be the range. Okay, and these alloys are formed by the atoms with metallic radius that is almost 15 centimeter of each other, the way I explained just now. Okay, now if you see in transition metal, we have seen that these metals have similar radius. Copper, zinc, they have similar radius. Since they have similar radius, you can form alloy with them easily. Because see, the alloy formation, the main catch here is similar radius, right? Because you have to, the new atom should replace the existing atom, so it should fit, because there is already lattice here, right? So if you want to remove this red ball with one more ball here, so this ball should actually fit in this place, right? So this ball should be plus minus 15% of this ball, correct? And this feature is there in transition metal. Most of the metals, they have almost similar atomic size. Since they have similar atomic size, they are fit to form alloy by mutual substitution. For example, brass is made from copper and zinc. Bronze is made from copper and tin. And these alloys have different property altogether, and they have huge industry application. We have seen the brass and bronze has been quietly used in the industries, and because they have different properties. So now with this, let's do a quick recap. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.